Hi everyone. Today's notes is notes 2.4. We are going to talk about parent functions, which are going to be really important as we move forward in this chapter and this semester, and piecewise functions. So our objectives here are to be able to graph these parent functions and piecewise functions, and then to write absolute value functions as piecewise functions. What we're doing here should look familiar to you. You should be like, oh yeah, but there's definitely some things that we did not do a lot of in Algebra 2, and I'm going to maybe teach it a little bit differently. It may be a little bit more of an extension of what you did in Algebra 2 as well. And so definitely going to be some important information as we move forward. If you want some graph paper, there is some graph paper located again in the class info folder. It's the folder 0. So if you want to pause this video, and if you have the ability to print that, you can. I believe you can also maybe download it, and then you could write on it with your EMR pen. I don't know for certain about that, but that might be an option for you as well. If you download it to your Google Drive, and then you could be using it there. But what we're going to start with is we are going to start with parent functions, and you are expected to know these parent functions. We're going to be talking about 3 points on each of these parent functions, or 3 important parts of them. And we will actually be taking a very quick parent function quiz using your EMR pen. We will be doing that in a few days, so make sure you check the calendar for that. And really it's just going to be a timed quiz. I'll give you a little extra time with the EMR pen. And you're just trying to identify the general shape. So we're talking a minute and a half, okay, is what you're doing. So here's what you'd be expected to do on that. If I gave you the equation y equals x, you should know the shape of that graph. Hopefully you're thinking in your mind that that's a line. It's a line through the origin that has a slope of 1. So the 3 points you would graph would be 0, 0, 1, 1, and negative 1, negative 1. And this was actually on an assignment that you guys had back in chapter 1. It was talking about being perpendicular to this line. So you would be expected to have those 3 points, and then you would be expected to show that that line would continue forever with arrows on the end. Now, as you're graphing this with an EMR pen, or even if we were graphing in person, I would not expect that to be a perfect line. So again, for time's sake, you would just have to show these 3 points, and then you would have to show that you're making a straight line. Y equals x squared, you guys should know that that's a parabola. Again, the vertex is 0, 0. 1 would be at 1, and negative 1 would be at positive 1. So again, you're not going to have time just to sub in numbers. The expectation here is that you know the general shape of this. So yes, 2 should be at 4. You can see that I'm a little off, but again, I'm not going to be counting off on that. I'm going to be looking for these 3 points and the general shape. Okay, the next one, y equals x cubed. Y equals x cubed, an odd function, 0, 0, 1, 1, negative 1, negative 1. So this one we looked at when we were in Algebra 2. Again, we're going to talk a little bit more about it tomorrow in the next set of notes. But something I do want to mention, okay, y equals x is considered an odd function because it has origin symmetry. Y equals x squared is considered an even function because it has y-axis symmetry. Y equals x cubed is another odd function because it has origin symmetry. And that does happen for the parent functions, guys. When the exponents are odd, they're odd functions if they're parent functions. If the exponent is even, they're even functions. That only happens for the parent functions, that you can just say that definitively. Y equals the square root of x would be 0, 0, 1, 1. So notice those 2 points have been on everything so far. But it can't be negative because the square root of a negative number is imaginary. So if you were in class, I'd be asking you what's another good point to use. And the point would be 4, 2. Because you'd want a perfect square. The square root of 4 is 2. Okay, and since the square root is in the equation, there's only one answer. It's called the principal square root. So 9 would be at 3. Again, I'm not going to be critical that you get through all those, but you should definitely be getting through these 3 points. Okay, the next one is y equals the absolute value of x. So 0, 0, 1, 1, and negative 1, 1. This is the same 3 points as we had on a parabola. The difference is these should be lines. Absolute value, we're going to talk about more later today in this chapter. See, I didn't do a very good job on the left side, and that would be okay. But since it's in my notes, I'll try to be better. But it's a straight lines. It's 2 pieces of lines, really. That's what it's formed from. Notice that that one is also even. It doesn't have an even degree, but it's still an even function. I didn't mention anything about the square root of x. The square root of x would be neither. It doesn't have any symmetry. But y equals the square root of x is an even function. Y equals 1 over x. Well, 0 can't work. 1 divided by 0 is undefined. So you might recall from Algebra 2 that 0 gets a vertical asymptote there because you can't divide by 0. 1 would be 1 and negative 1 would be negative 1. You're also going to be expected to graph a horizontal asymptote at y equals 0. So it has these two asymptotes, and then this was a rational function, so it has these things called branches. So they're going to approach the asymptotes here. This is another odd function because it does have origin symmetry. So that's probably the weirdest one because, again, you have to get the asymptotes for that one. So you'd be expected to have these 2 points and then the 2 asymptotes. And the last one would be the cubed root of x. Now, this is a cubed root, so the cubed root of 0 is 0 and the cubed root of 1 is 1. The cubed root of negative 1 is negative 1. So it has the same 3 points that y equals x cubed has, but when it's the cubed root, it's just that on its side. It's just like the square root is half of a parabola on its side. That's because of the imaginary numbers. This is what you would have for a cubed root. So again, you will be taking a parent function quiz. What it will be again is it will be these 7 graphs in a random order. They're not going to be in the same order. You will be timed, okay? And you will be expected to just graph the general shape. You're expected to give the 3 points on the graph. Or again, if it's the rational, the 2 points and the 2 asymptotes. That's what you would be expected. Again, it does not have to go perfectly through those, but again, it will be timed. Okay, so you'll get at least 90 seconds. It may give you a little longer, we'll just see. But typically you would get about a minute, so should be plenty of time. So you can always practice that on your own. Just put them randomly on a piece of graph paper and see if you can get those down. So I'll put quiz there. So easy 7 points, hopefully. That's the goal. Okay, so we're going to graph some piecewise functions. So that's talking to us about how to graph parent functions. So we're going to get into piecewise functions. So really what you had in Algebra 2 is you would graph a piecewise function that had 2 pieces typically, and all they had were inequalities, and they typically were linear or quadratic. Well, we're going to add some of any of these 7 parent functions to the mix. So you'll see here our function f of x equals 2x plus 2 whenever x is between negative 3, including that, and negative 1, not including negative 1. It's going to be 4 whenever x equals negative 1, and it's going to be the absolute value of x whenever x is greater than negative 1. I want you just to think about the shape of these graphs. Don't worry about, these are just our kind of restrictions. Those are the intervals that we're going to graph this on. But this first one, hopefully you know that 2x plus 2 is going to be a diagonal line with a positive slope. Okay, 4 is going to be constant or a dot. Okay, so in this case, it's only got one value here for x, so it's just going to be a point. And then the absolute value of x is going to be a v. And again, there's nothing else except for the parent function. So the way that I'm going to do this is the way that I teach it, is I go through and I make 3 tables. So I'm going to have table 1, table 2, and table 3. And I'm going to make 3 tables of values. Now you can do this a variety of ways. Okay, this is one way that just should work for everybody. So for table 1, I'm going to make a t-chart, and I have to pay attention to these right here, negative 3 to negative 1. Since it has 2 values, negative 3 and negative 1, I'm going to put both of those values in the table. So I'm going to put negative 3 at the top and negative 1 at the bottom. I need another point, so I'll just pick a point between it, negative 2. Now, negative 3, it says x is greater than or equal to negative 3 if I read it from right to left, or negative 3 is less than or equal to x. Well, the equal to means this is going to have an endpoint that is filled in, and then it's got to be less than negative 1. That's going to have an endpoint that is open. Even though it says less than negative 1, I realize that 1 is not less than negative 1, but it still serves as an endpoint. So I still need to put it in my table if it's in my equation. So then we're just going to sub these values in. So if I sub in a negative 3, 2 times a negative 3 is negative 6, plus 2 would be negative 4. Okay, so you should be able to do the other one. Sub in a negative 2. Sub in a negative 1. And you should get those 3 values. So those are just ordered pairs. So then on my graph paper again, negative 3, negative 4 is going to be an endpoint that's closed. Negative 2 is not an endpoint, but it's still a closed circle. I mean, it's just a point on the line. And then negative 1, 0 is an endpoint, but it's open. So the endpoints are the ones that get open and closed circles. Everything else is just, this line consists of all these dots on this line. Okay, all those make it true, so that's why it fills in the line. Okay, so again, open and closed circles only go on endpoints. So there's the first part. That's the first piece. Notice it was a line, had a positive slope, has a slope of 2, up 2 over 1, up 2 over 1. If we were to keep going up 2 over 1, notice it would have a y-intercept of 2. It's just that we don't go that far because the domain for that does not include 0 for x. Okay, it stops at negative 1. So then for the second part, it just says when x is negative 1, y is 4. You could make a t-chart for that, but the only thing you would have would be negative 1. It says it's equal. So we have the point negative 1, 4. So negative 1, 1, 2, 3, 4. Let me label our graph a little bit. It's always a good idea to label the graph. I haven't done a good job of doing that for you guys. Maybe this is the first time we've graphed. Maybe I'm thinking of a different class, but it's always a good thing to label a little bit. So that's just going to be a point. And then the last one says the absolute value of x. So it says whenever x is greater than negative 1. Again, even though it says greater than negative 1 is going to serve as an endpoint. So I want to pick negative 1, and then I want to pick numbers greater than negative 1. So the absolute value of negative 1 is 1, the absolute value of 0 is 0, the absolute value of 1 is 1, the absolute value of 2 is 2. So this is going to look like our parent function. It's just a piece of it. That's why it's called a piecewise function. So negative 1, 1, I didn't put this in here, but notice it says greater than that, so we're going to have an open circle there. So at negative 1, 1, we're going to have an open circle. 0, 0 is on the graph, 1, 1's on the graph, 2, 2's on the graph, so this is going to be a V. But again, it's just part of a V. It looks more like a check mark. Has one endpoint and one arrow. Now what you need to notice here is if we were to take a vertical line and we were to drag this vertical line through this graph, it should only touch every point one time. And what comes in question is right here at negative 1. Okay, notice it's touching, it looks like it's touching 3 points, but only one of those 3 points is filled in. The other 2 are open. So it does pass the vertical line test. Also notice that there are no gaps. So we're not going to go to negative 2 and 0 because from the first and third one. Otherwise, we would have gaps. There should be no gaps. Basically, when you get to negative 1, if you were on the red line, you could take an elevator up to get to the green point. You could take an elevator back down to get to the purple, and then you could continue on your journey. Okay, that's kind of the idea. So if I just follow this, here, I'll just give it a point. So if I follow this star, okay, this star could follow here, could get here. It's like up elevator, get up to this point. Okay, elevator, get to this point, and then go. Okay, so I shouldn't have to jump to get to any point. Okay, it should be nice and continuous. So that's how we would graph that piecewise function. Going to be asked to state domain and range. So domain would be x's and range would be y's again. So what are our domain values? What are our possible values for x? Well, if we look, again, from left to right, I'll put an actual line in here so it's actually straight. Maybe. There we go, move that line. So the first x value we come to is negative 3. Okay, so that's going to be the start, and it can touch negative 3. It has a closed circle. So negative 3, and we're going to keep going. If we keep going, it's still here. That gives us negative 1, still gives us 4. We keep going, and that arrow keeps going. So it would be negative 3 to infinity. And then for the y values, if we just take that and we make it horizontal, we're going to go low to high. So for the low values, again, this is why it's good to mark our graph a little bit. So that would have been negative 3, negative 4. So the low value would have been negative 4 there. So it's filled in, so it's going to have a bracket. We keep going. It can have 0. It has 0 right there at the origin. Keeps going. We still have points on the right side there, and this is going to keep going because of that arrow. Okay, so our range would be from -4, again, to infinity. So that's how we'd find domain and range of that. So that's graphing it from an equation. Let's take a graph and write the equation. So now we're going backwards. So here's where you're going to have to identify your parent functions, if you have any. It looks like we have an absolute value function that's been flipped over, and we're going to talk about being flipped over tomorrow. But if you notice the slopes, you got to make sure you have the same slope for it to really be absolute value, and it does not have that here. So I'm just going to start here on the left. I'm going to start from here to here, and that's a line. So to find the equation of that, to be able to write it as a piecewise function, again, you guys did this in Algebra 2. What we need here is let's pay attention to our notation here. But what we need is since it's a line, we need the slope and we need the y-intercept. Remember, the y-intercept can be called b. So if we find the slope, we need to make sure we're going through 2 points on the graph. Since I don't exactly know where the points are, I'm just going to go from this bottom point to this top point. So up 1, 2, 3, 4, 5, 6, up 6, right 1, 2, 3, 4, right 4. So my slope would be 6/4, which is 3/2. My y-intercept, if I count, would be at 6 here. So this equation would be y equals m slope x plus b y-intercept. So as I write it in my equation here, I'm going to move this so I have, not everything, but I want to move this so I have a little more room. So as we write this here, we wouldn't have the y equals because the y equals comes from f of x equals, so 3/2 x plus 6. Now, when does that occur? What x values does that occur with? So if we look at our x values, okay, it starts here, so that's when the x value is -4, and that ends here when the x value is 0. So we would say it's going to be that from -4 to 0. And then we're going to figure out if they're going to be equal to. Since the first one has a closed circle, we're going to put equal to. The second one, it's connected, so we don't know if it's open or closed, but one of them needs to be closed. So I'm going to go ahead and put an equal to there. We'll talk about how you could have put that second equal to on the next one, but I'm just going to go ahead and put it with this one so I don't forget. So now I'm going to look at this graph, this next graph. So I'm going to act like this next graph has an open circle and an open circle. We know it has an open circle on the right, but I'm going to go ahead and use an open circle on the left since I closed it in with the red one. So that's another line. So I need the slope and I need the y-intercept, or the b value. So again, if I do slope, I'm going to go down 1, 2, 3. So that would be -3 because I went down, and over 1, 2, 3, 4. So my slope would be -3/4. My y-intercept is still 6. So this is the equation. You guys should be able to write that, -3/4 x plus 6. So we're going to write that in our piecewise function. Notice the notation. F of x equals y equals these 3 pieces. So when does it equal this piece? Well, again, it's going to start here at 0. I'm not going to include the 0. That's why we used an open circle up here, okay, on the blue line. And then it's going to end here at 4. And again, that's an open circle. So it's between 0 and 4. So you can either have the line for the equal to here, or you can have it here for 0. It can only be in one place, though. Okay, it should only be in one place. Okay, the last one is this filled in circle here, and then it's just a constant. So remember, when we have a horizontal line that has a slope of 0, if we were to bring it back over here, it would have a y-intercept at 6. So it would be y equals 0x plus 6, but we can simplify that to just be y equals 6. If we were to extend that line, guys, through the entire graph, okay, it would just be a line, a horizontal line that touches the y-axis at 6. Okay, so the last thing, we already have y equals, so we're just going to put a 6, and when do we get 6? Well, again, it comes back down here. It starts at 4. And it continues to the right. So whenever x is greater than or equal to, it's filled in 4. So there is our piecewise function. Again, you need to notice the format of that. Something I will mention is if you were to pick any value, let's say we were to pick, f of any value from -4 to infinity, because that's what our domain is. Let's say we were to pick f of 3. If you were to go up here and evaluate, 3 is between 0 and 4. Oh, that's not going to be a nice one because it's going to be a bunch of fractions. Let me pick a little nicer one. Let me pick f of 2. So if I were to pick f of 2, it's still in between 0 and 4, so I would sub it in. -3/4 times 2 plus 6. So if we did that, we'd get -6/4. You could use a calculator. -6/4 is -3/2 or -1.5. Okay, -1.5 plus 6 is 4.5. So at 2, right here, we should be at 4.5. 1, 2, 3, 4.5. So you could just check to make sure it's actually on your line. And you could check one in each section and make sure you'd actually get it on those pieces of the graph. So that's writing an equation from a graph. Again, review from Algebra 2, but it's been a while. You would have done that about this time last year. The last thing we're going to talk about is how to write an absolute value equation as a piecewise function. So that's our last objective, write absolute value functions as piecewise functions. So we're going to start with what is the definition of an absolute value. Okay, so you'll see here f of x equals the absolute value of x. Well, the definition of an absolute value is that it's going to equal x whenever x is greater than or equal to 0, and it's going to equal the opposite of x whenever x is less than 0. We're going to use this definition today. So this would be by definition, this is what's true. So think about what that graph looks like. Okay, it's going to be positive y equals x whenever x is greater than or equal to 0. It's going to be the opposite of that, so negative x, whenever x is less than 0. And again, that's because the first one is closed and the second one is open. They're just connected there. So how are we going to rewrite f of x equals x minus 2? We need to know how to rewrite that as a piecewise function. That's what it's asking us to do. So right now it's an absolute value function. We want to rewrite it. So here's what we're going to do. You may have done it a little different in Algebra 2. You may not remember it at all, and that's okay because it was a long time ago and you probably never did it again. But this is something that you do take with you and could use in calculus or in even college algebra. So what we're going to do is we are going to first find what we call a breakpoint. Now a breakpoint is basically a vertex. I'm also going to call it a critical value. We use critical values in the first chapter whenever we were solving equations. So that's what we're going to find. A breakpoint or a critical value. Maybe you abbreviate it BP or CV later. So how we're going to do that is we're going to take what is inside the absolute value and we're going to set it equal to 0. So that's pretty easy. We get x equal to 2. We're going to take that and we're going to put it on a number line. And I'm going to write x minus 2 because that was what was inside the absolute value. I'm going to write it outside or out to the side of the line. The reason I'm doing that is I am going to sub in test values into this point, or into this expression, I should say. So we're going to use this to sub in test values. So I'm subbing it in only to x minus 2. So let's say I pick 3. If I sub in 3 to x minus 2, I get 1. What I'm concerned about is that I get a positive number. So to the right of -2, I'm getting a positive number. If I sub in 1, 1 minus 2 is -1, so I'm concerned that I get a negative number. So now I'm going to look at these two pieces. And by definition, it says, back up here, it says that our function, our piecewise function, is going to equal x. X is what is inside the absolute value. So we're going to say it's going to equal x minus 2, okay, whenever we have values that are greater than or equal to 0. Now, how we're going to use this number line there. Because again, this 0 changes because we've just translated this function. So what we're going to do, it's going to be the exact same thing that we started with whenever we're on the positive side here. So that is when x is greater than 2. So we're going to say when x is greater than or equal to 2. It doesn't matter which one you put the equal to on. I'm just going to put it at the top. Okay. To get the next part, you'll notice the minus here. Okay, that's when it's the opposite. That's when it's the opposite of x. Remember, x is what's inside the absolute value. So I'm going to show that a little work outside. So we're going to do the opposite of what is inside the absolute value. So if we simplify that, we get negative x minus 2. So it's going to be negative x. I don't know why I changed that. Let me back up. Should be the opposite of x minus 2. My apologies. So it should be negative x plus 2. Because both signs changed. Now that's going to occur, notice when the minuses occur, the opposite occurred whenever the numbers were less than 2. So that's going to occur when x is less than 2. So that is how we would write this particular absolute value equation as a piecewise function. Here's kind of what's going on. Well, actually, instead of graphing it, since we're going to do that tomorrow, I'm going to graph it in Desmos. So y equals the absolute value of x plus 2. Let's get a new graph. Okay, I'm just going to shut these off because I don't know how to get rid of it right now. So y equals the absolute value of x. So here's y equals the absolute value of x. We know what that looks like. So I'm going to do x minus 2. And we're going to talk more about this tomorrow, but notice it shifted to the right. So what I have is I have this positive line, what we just called it, okay, we just called it in our piecewise function was x minus 2. So if I graph y equals x minus 2, you will notice that I have the right side of this graph. Now it keeps going because I only want that part whenever x is greater than or equal to 2. Okay, and I don't recall how to do this. Let's see if this works. Nope, I don't. There's a way to get those restrictions, but I don't remember off the top of my head. For the other one, it would be y equals negative x plus 2. So let me see if I can change that color so we just see a different color here. So that's the green one. So again, that only occurs whenever x is less than 2. So again, if I could write on this, we're basically taking off those parts, and that's how I'm getting that graph. That's how I'm getting that original graph there. Okay, those two pieces that have been restricted, okay, those two pieces of lines. That's the idea of what we're doing here, okay? Now, this one's pretty simple because there was nothing outside the absolute value. So we're going to look at one of those, and then you're going to have some practice on this. So we're going to write this one as a piecewise function. So we have f of x equals 3 plus the absolute value of 5 minus 4x. Now, to make this a little easier for me, maybe you don't need to do this, but I'm going to put the absolute value first and put the 3 at the end. Don't have to do that, but that's what I'm going to do. So we need to find the breakpoint or the critical value. And the way that we do that, again, is we only look inside the absolute value. It's basically the vertex of the graph, or part of the vertex of the graph, I really should say, the x value of the vertex of the graph. So 5 minus 4x equals 0. This is the breakpoint where the vertex would change from increasing to decreasing. That's what's happening. So we're talking about this x value that would be part of the vertex. We're not concerned about the y value because the y value doesn't affect the domain restriction. Okay, we're only worried about the x. So if we solve this, we're going to subtract 5, or you could add 4x, divide. We're going to get positive 5/4. Okay, that's our critical value. So what are we going to do with it? We're going to put it on a number line. We're going to put the 5 minus 4x out to the side because we're going to test values only using what was in the absolute value. So I'm going to test a value over here. So 5/4 is 1.25. So let's say I test 3. 5 minus 4 times 3 is 12. 5 minus 12 is negative 7. So that's negative. Then I'm going to test something over here. Let's say I test 0. 5 minus 4 times 0 is 5. That's positive. So notice this is opposite of what we had before. So what this is telling me is I write my piecewise function, f of x. We're going to have to show a little work down below. Okay, this is saying here I'm going to take the negative whenever the opposite of what's in the absolute value, whenever I'm greater than 5/4. Remember, this would be x is greater than 5/4 or greater than or equal to. You can always keep the equal to on one of them. Okay, and this side would be whenever x is less than 5/4. So I'm just going to use the positive part of the absolute value. So I'm not going to change it. Again, this is by definition. Remember our definition back here is the x and the negative x. Okay, the original and the opposite. So I'm going to have to show some work. So I'm going to do the positive side first. You can do whichever side you want. I'm going to do the positive side first. The positive side says you were going to take out of what was in the absolute value just the way you saw it. So we have 5. I'll actually write it up here. 5 minus 4x. And then we have the plus 3. Now we're going to have to simplify that in a moment. But that occurred whenever x is less than 5/4. And again, you can say less than or equal to. It does not matter. As long as one of them has an equal to, you're all good. Because they're connecting at that vertex. Okay, for the negative side here, okay, that means you're going to take the opposite of what was in the parentheses, or in the absolute value, excuse me. What is outside does not change, so it's still plus 3. And that's going to occur when the x values are greater than 5/4, because that's when we got the negative. Okay, the opposite here in front happened whenever we were greater than 5/4. So you are going to have to simplify that. So it's just a matter of distributing, combining like terms. Don't forget the equal sign. For some reason, we always forget the equal sign. That's like y equals. So you can rewrite it, but again, 5 minus 4x doesn't have to be in parentheses there, plus 3. So 8 minus 4x, or you could say negative 4x plus 8, doesn't matter. Whenever x is less than 5/4. Again, this restriction here is coming from this breakpoint critical value. That's where it's coming from. Again, it's the x value of the vertex of this graph. For the other one, this would be negative 5 plus 4x plus 3. So that would be positive 4x minus 2. Whenever x is greater than or equal to 5/4. Again, the equal to does not matter which one you put it on. You just put it on one. Again, if I was to graph this in Desmos, just to give you a picture of what's going on, I'll take those two off. So we have 5 minus 4x. Get that 2 out of there. Plus 3. Okay, here's our graph. So then I can simply just check. If we had negative 4x plus 8. Okay, notice that's the left side of the graph. That was when x was less than 5/4. So if you click on this point right here, shut this off. If I click on that vertex, notice it's 1.253. That's that vertex. So this part here, this green part, is the left side of that. That's when x was less than or equal to less than 5/4 or less than or equal to. Okay, if I type my other one in, y equals 4x minus 2. Again, that's the right part. Okay, that's when x was greater than 1.25 or 5/4, greater than or equal to. So that's how we got the two pieces. So trying to visualize it as well, but knowing the algebra to be able to get us there. Okay, that's definitely going to take some work. So you have a Schoology assignment for that where you're going to practice that. I would expect to see what you see here. I would expect to see the breakpoint critical value. I expect to see the number line where you've tested some values. And then obviously I would expect to see the final answer, and you can check those. Okay, now if you don't have a calculator on this, like let's say this is on the no calculator part, you could still check values. You could check f of 0, and maybe you check f of 8 or f of 3. We'll do a smaller one. Well, f of 0 is less than 5/4. So if I subbed it in here, I would get negative 4 times 0 plus 8, which is 8. Well, sub it back up here in the original. If I sub a 0 in there, I get 5 minus 4 times 0, which is 5. The absolute value of 5 is 5. 3 plus 5 is 8. That checks. And then check f of 3. So 3 is greater than or equal to 5/4. So 4 times 3 is 12. 12 minus 2 is 10. And then check it back up here at the top. We would have 3 plus the absolute value of 5 minus 6, or 5 minus 12. Well, 5 minus 12 is negative 7, and the absolute value of negative 7 is 7. So 3 plus 7 is 10. So that checks out. So you can always check it. Again, you could check it graphically, okay, on Desmos or graphing calculator, but you can also check it algebraically. So that's what we've got for 2.4 notes. Again, please let me know if you have questions. I miss being able to have a dialogue with you about this. So don't hesitate to ask. We can definitely have some conversations during a meet. That would be great. So have a good day, guys.